Alright, so this is going to be part 3 of section 3.4, and I'm going to graph E functions in this video. I don't think I'll get every E graph done, and so there'll be a couple that I'll post up on the screen for you to do. This is at least my third attempt at doing this video, and when I wrote the problems, I kind of have an idea of the solutions in my head, but not a complete idea, and at least maybe not completely correct. And as I go through and do the graphs for the E functions, I'm going to skip one of the instructions because it doesn't really fit in a brief calculus class. When we just did the graphs of fractions, we found vertical and horizontal asymptotes. And some E functions have vertical asymptotes on their graphs, some have horizontal asymptotes on their graphs. It turns out that none of the E functions that we're going to graph have vertical asymptotes, so we couldn't find something that didn't exist. And the ones that had horizontal asymptotes, they all don't have horizontal asymptotes. The ones that have horizontal asymptotes, the calculus strategy that you need to use to find the horizontal asymptote is something that you teach in Calc 2, and it's something we don't have. So we're going to skip doing any asymptotes for the E functions. But when we get to the test and do the fractions, we still have to do the asymptotes for fractions. But even on the test, if I give you an E function and ask you to sketch a graph and find the features of the graph, I'll just delete this part. It won't be on there. So the first function I have is problem 22, f of x equals e to the 2x squared. The domain is the first feature I'm asked to comment on or find. And just like polynomials, there aren't any values for x that a generic E function would be undefined. To get a value of x that would make an E function undefined, it wouldn't be the E part that would cause to have a glitch in the domain. If I had a function like e to the x over x minus 5, this function would have a restricted domain, not because of the E part, but because of the x minus 5 in the denominator. This function would have a domain of all real numbers except 5. So in general, E functions have domains from negative to positive infinity, unless there's a feature from another type of function fused together with your E function that would cause the domain to be restricted. And in our problems that we're going to do here, none of the E problems have restricted domains. There's going to be no algebra at all to do for any of the domains of the E problems. So when we get to the test from section 3.4 of chapter 3, if you're asked to find the domain, the only kind of problem the only kind of problem that we've done so far in 3.4 that has a domain other than negative to positive infinity are the fractions. I want to say that's the case on the test. I haven't written the test yet, and it's been so long since I've done section 3.1 that I forget if there's some square roots in there that have domain restrictions. But E functions and polynomials don't have any domain restrictions. Their domains are just all real numbers. To do the X-intercept part for 22, to do 22b, the X-intercept, to find any X-intercept, you just take the function and set it equal to 0. There are shortcuts to find the X-intercepts of fractions, but this long method, setting the entire function equal to 0, is the perfect strategy for finding any X-intercept. And we've done this a few times already in this chapter and in earlier chapters. E to some power can never be equal to 0. This won't have a solution because e to any power can never be 0. And because this doesn't have a solution, the algebra for finding the X-intercept doesn't have a solution, then there just isn't any X-intercept. For part C, just because the graph doesn't have an X-intercept doesn't mean it doesn't have a Y-intercept. To find an Y-intercept, you just take 0 and plug it in for the x's. So I went to the original function, f of x equals e to the 2x squared, changed that to a 0 and that x to a 0. That I can do in my head, but I'll do it on my calculator just in case you can't do it in your head. So I'll turn my calculator on, clear any junk that's in there, and I'm going to go second and ln to get the e function, and then 2 times, and then parentheses 0 squared, and then close out another parentheses. So what I have to do when I pull out my calculator to do this, I have to put the entire exponent in a parentheses. And because I had the 0 in the parentheses, I've got 2 sets of parentheses. And this gives me 1 for the y-coordinate of the y-intercept. If I did this by hand, the exponent would be 2 times 0, because 0 squared is 0. That would give me e to the 0 power, and anything to the 0 power is 1. So the y part of the y-intercept is 1, and the x part of the x-intercept is going to be 0, because always when we're finding an intercept, the opposite letter that we're finding the intercept for is going to get a 0. So I'm finding the y-intercept, so the x part has to be 0, and the algebra gave me y equal to 1. That's the first feature I could show on a graph, and when I go to show this on a graph, I'm going to make my graph a little bit top-heavy. I have lots of room for positive x's and maybe not so much room for negative x's, because e functions, they usually are top-heavy. Usually they don't even exist at all below the x-axis, and they go super high on the y-axis. So I need to plot the y-intercept, which is a point 0, 1. And when I go to plot the y-intercept, then I'm committing to making a mark on the y-axis, and I'm choosing how to scale my y-axis. And I don't know if I really need to scale my y-axis by 5s, by 10s, by 20s. I'm going to scale my y-axis by 1s and put the point 0, 1 in there, and I might regret that in a little bit, because maybe I'll need to get to y equal 100. And if I have to get to y equal 100, I might have to throw this graph out and recalibrate. All right, so there's the y-intercept. The asymptote parts for section 3, the problems on the e's in section 3.4, we're going to skip. Now we're into the increasing, decreasing maximums and minimum part. And for the increasing, decreasing maximum and minimum part, I need the first derivative. I'm going to do a lot of work on my calculator, but not all of it. So for part 22e, the interval where the graph is increasing, 22f, the intervals where the graph is decreasing, and 22g, the breakdown for the relative maximums and relative minimums, all need the first derivative. Haven't found the derivative yet, but it's not so hard to find. So the original function, it's off screen right now, so I'll pull it back for you. It's f of x equals e to the 2x squared. I need to find its derivative, and e functions are just about the easiest functions to find the derivative of. The e function's derivative, you just take the e function and multiply it by the derivative of its exponent. So I wrote the initial e function down, and next to it, preceding it, I'm going to write the derivative of the exponent. To find the derivative of 2x squared, I take the exponent 2, multiply it by the coefficient 2, and get a 4, and lower the exponent from x squared to x to the first power. And I won't write that 1, but 4x is the same as 4x to the first power. So that is the derivative of, or the first derivative for the function. And now I need to find critical numbers. And for e functions, since they're defined everywhere, it's generally enough just to set the first derivative equal to 0, and that will give you all the critical numbers that you need to have. So my e derivative is 4x e to the 2x squared. It's factored. I'm finding critical numbers by setting it equal to 0. Since it's factored and set equal to 0, I'll just separate the two factors and set each one separately equal to 0. For the 4x equal to 0, I don't probably need to show the algebra, but the algebra to get the critical number would be divide both sides by 4. That's going to give me x equal to 0. And then the e to the 2x squared equal to 0, e to any power can't equal to 0, so I'm not going to get a critical number for that. So the only critical number that I get is 0, and when I go to do my number line work for the maximums, minimums, increasing and decreasing. I'll create a number line. On the far left edge of the number line, I put negative infinity. On the far right edge of the number line, I put positive infinity. Between the infinities, I put 0. Then I create intervals, and I always get one more interval than critical numbers. I have one critical number, which means I need to get 2 intervals. The intervals are going to be negative infinity to 0 and 0 to infinity. And for increasing and decreasing and for concavity, the intervals only get round parentheses as opposed to square parentheses. Now in each interval, I need to pick a number and plug it into the first derivative. In this interval, it goes from negative infinity to 0. There's only negative numbers I'm allowed to pick. I'm going to choose x equal to negative 1. I'm going to find out what f prime of negative 1 is. In this interval, from 0 to infinity, you can pick any number bigger than 0. I'm going to pick x equal to 1. I need to find out what f prime of 1 equals. And all through this section, we've been using the dy dx feature of our calculator to do this. So I'm going to enter this function, f of x equals e to the 2x squared, in my y1. So f of x equals second and ln for the e, and then 2x squared, close that parentheses. I don't think a zoom standard window is going to be the best window for our final graph, but it will be adequate for the increasing and decreasing part, because all I need in my window is my x's to be, my x min to be less than negative 1 and my x max to be bigger than 1, and I will get a, well, all I need is my x min to be an x max to cover up 0, which is a critical number. But since I'm picking negative 1 and 1 to check, as long as my x min and my x max covers up negative 1 and 1, it's not going to have a problem checking for me. So I'm just going to hit zoom standard. That was kind of a clunky explanation. Sorry about that. And oh, it actually gave me a decent enough picture. So that I might have to modify the window for my final graphing part of this. But finishing up here, I'm going to do second calc, dy dx, type in negative 1, and I get negative 29.56. And again, if you didn't even write down a number and you just wrote negative down, that would be adequate, because we don't care so much about the number, we just care about its sign. Because that came out to be negative, in this interval the graph is decreasing. I'll put a little down arrow above the number line to show that decreasing. Move over to the next interval, go second calc, go down to dy dx, type in 1. Messed up somehow. Second calc, dy dx, type in 1, and I get 29.56. Again, I don't worry so much about the 29. I just worry about whether it's positive or negative. And since this is positive, in this interval the graph is increasing. And so I'll put a little up arrow in that interval. So now I can answer the part where the graph is increasing and decreasing, and I see that this function has a minimum value and its x coordinate is 0, and I don't see any arrows that point to a maximum, so for the relative maximum there won't be one. So to finish up some of my answers, for increasing, the graph is increasing in the interval 0 to infinity. For decreasing, it's decreasing in the interval negative infinity to 0. I don't see any maximums, so for the maximum part of this, there's going to be none. I do see a minimum, and its x coordinate is 0. I'm going to try to box in the minimum answer right here. So I'm going to say there's a relative minimum of y equals some number, which occurs when x equals to 0. In one of the videos, when I was writing up this little sentence, I started putting periods where they probably shouldn't be, but it's not an English class. I didn't redo the video because of my grammar error. So if I want to get the minimum part finished, I like to be able to use the value feature on my calculator to find the y coordinate. And if when I plug this x value using the value feature into the original function, if the y isn't a decimal, then my calculator's answer is suitable. So if I go second calc value, type in this x value, when I hit enter, I get a non-decimal answer, then I don't need to do extra work to find that y coordinate. So finishing up the answer for the relative minimum, there's a relative minimum of y equals 1, which occurs when x equal to 0. If I wanted to get this 1 by hand, I would take the original function, f of x equals e to the 2x squared, and plug in 0 for x. So I'd go f of x equals e to the 2 times 0 squared, and that happens to be the same computation that I did when I found the y-intercept. It's just a fluke that the critical number is at the same value as the y-intercept, so I did that computation already. Alright, so that's everything for E, F, and G. On my sheet here, I'm going to just emphasize to myself on my graph that it's increasing from 0 to infinity, and it's decreasing from negative infinity to 0, and we have a relative minimum at the point 0, 1. I've already plotted the point 0, 1 because it's a y-intercept. I don't need to replot it. Alright, so a little bit more to do before we can finish this up. The rest of what I need to do before I graph is h, I, and j, the intervals where the graph is concave up, concave down, and any inflection points. And so in order to do h, the interval where the graph is concave up, I, the interval where the graph is concave down, and j, the inflection points, I have to know the second derivative. And in order to define the second derivative, I need the first derivative. I might need the original function here, so I'm going to write down the original function, which you can't see, f of x equals e to the 2x squared. And I'm going to need the first derivative, f prime of x equals 4x e to the 2x squared. So I just stole those from work that I already did because I need for concavity the second derivative. So now I'm going to find the second derivative, and there's multiplication here. And when I have multiplication, I need to use the product rule to find the derivative I'm searching out. So I'm going to use the product rule. I'm going to take the derivative of 4x and multiply that by e to the 2x squared, put a plus sign down, and then take the derivative of e to the 2x squared and multiply that by 4x to use the product rule. So the product rule requires me to take the derivative of each of the factors times the other unchanged. For this derivative of 4x, because it's a first power term, its derivative is a coefficient of 4. So the first part of my product rule is going to have 4e to the 2x squared. And then for the derivative of e to the 2x squared, that's what it is. It's 4x e to the 2x squared. But to find its derivative, you just take the derivative of its exponent, which is the derivative of 2x squared, which is 4x, times the e to the 2x squared function unchanged. So this is the derivative of that, and I still have the times 4x. I certainly could multiply these 4x's out right now, and it wouldn't hurt to do that, but there's a common factor, and sometimes if I pull out the common factor before multiplying things out, it makes my work a little bit easier to follow. So there's a 4 on either side of the plus sign. I can factor one of the 4's out from the right of the plus sign, but not both of them. And there's an e to the 2x squared as a common factor on either side of the plus sign. So I'm going to factor those out and get 4e to the 2x squared written before a single parentheses. I'm going to have the plus sign that's between the factors or terms inside the parentheses. To the left of the plus sign, since I factored out the entire first term, I'm going to leave a 1 behind. And then after the plus sign, I have an x left and a 4x. And that x and 4x that haven't been factored out need to be multiplied back together. And x times 4x is 4x squared. That's factored, which is nice. There isn't any room in my answer to put what the second derivative is. In none of the steps does it say write the first derivative, write the second derivative, but I need those to get my answer. So now that I have it factored, I'm going to set each of the factors equal to 0. Well, I'm going to set the whole second derivative equal to 0. And now it's factored. I can set every factor equal to 0. I could set 4 equal to 0. I can set e to the 2x squared equal to 0. And I can set 1 plus 4x squared equal to 0. When I set the 4 equal to 0, it doesn't have an x, so it doesn't give a solution, doesn't give a critical number. When I set the e to the 2x squared equal to 0, e to any power can't ever be 0, so that doesn't give a solution, it doesn't give a critical number. And the 1 plus 4x squared is prime, it doesn't factor, so I'm going to need to solve it by square rooting. And so what I'm going to do is I'm going to minus 1 from both sides to set it up for my square rooting. That's going to give me 4x squared equals to minus 1. And then I'm going to divide both sides by 4. That gives me x squared equals negative 1/4. And now I can square root. And generally, if you introduce a square root to an equation that doesn't already have one, you need plus or minus on one of the sides. So I did x squared square root on that side, plus or minus square root on the opposite side. The square root of x squared is just x. I'm going to leave the plus or minus sign, and the square root of negative 1/4, because it's negative, you get an I, and the square root of a fraction is a fraction. I take the square root of 1, which is 1, put it in the numerator, the square root of 2, which is 2, and put it in the denominator. That says x equals plus or minus 1/2 I, and that is, in some sense, a critical number, but it's an imaginary critical number. And when I make my number line up and put critical numbers on my number line, there's no i's on a number line. Those are only real numbers. So this, even though it gives me a critical number, it's a non-real critical number, and it's not a critical number that's going to go on my number line. And so when I do my number line, the only numbers I'm going to put on it are negative and positive infinity. I don't get any critical numbers that can go on my number line when I do my calculus here. So I'm going to have a negative and positive infinity, and there's no room for i's between the infinities. So the only interval I'm going to have to check is one interval. I get no critical numbers. I get one more interval than critical numbers. One more than 0 is 1. I need to, into my second derivative, plug a number. I can pick any number, and I'm going to pick 0. And I'm going to do f double prime of 0, and that's disgusting, but I'll write it. I'll try to squeeze it in here. I'm going to go f double prime of 0, and f double prime is 4 times e to the 2x squared. That's going to be e times 2 to the 0 squared times 1 plus 4 times 0 squared. That's just taking that x, and that x, and plugging my 0 in. When I go to do this on my calculator, I know that 0 squared is 0, so I'm going to go 4e to the 2 times 0 times 1 plus 4 times 0, just to make it a little bit easier on myself. And the more work I do in my head, the less I have to type on my calculator. Let me try this real quickly. I'll go 4 times second ln e to the 2 times 0, and then close out the parentheses, and then parentheses 1 plus 4 times 0. And again, I'm only worried about the sign. If it's positive, the graph is concave up. If it's negative, the graph is concave down. I get positive 4 when I do this. So equals to 4. That's positive. So in this interval, the graph is concave up. And that's the only interval. Oh, I just had a glitch. So hopefully this stuff where I said f double prime of 0 equals to positive 4, because it's positive in the only interval that I have to check, the graph is concave up. So when I go to write my answer, I'm going to say the graph is concave up in the interval from negative infinity to infinity. positive infinity. The graph is never concave down. There's no intervals where it's concave down. I can say none or never. And because it doesn't change concavity, there's no inflection point. So unfortunately, I don't have a heck of a lot to transfer to my graph from either the first derivative information or the second derivative information, but I'll still piece together a decent graph. So it's concave up everywhere. It's concave down never. And there's no inflection point. So now I'm going to borrow most of the graph from my calculator, and I'll just make sure that it does what it needs to do. So when I graphed this with the standard window, I entered the original function, I did zoom standard. It actually gives me a graph that I think is suitable. So that graph I'm just going to copy. It looks like a parabola, and I'm going to copy this the best I can and talk through it. So in the interval from negative infinity to 0, it needs to be decreasing, and that's what's happening here. It's decreasing in this interval, and it needs to be concave up everywhere. So this graph is decreasing and concave up. It gets to the minimum point, and it gets really flat at that minimum point. And then at the point 0, 1, the minimum point, it turns around and starts increasing, but it's always concave up. It's never going to flip to concave down. So the graph that my calculator gave me, oh boy, does just that. It decreases from negative infinity to 0. It gets to the relative minimum point of 0, 1, stays concave up. After the point 0, 1, it increases and stays concave up. So the graph that my calculator gave me with the standard window would be adequate. If I wanted a more accurate graph for any special reason, then I'd actually have to make tables and plot more points, but we don't need to get that precise with our graphs. Okay, so now we're going to do 24. So you should go back and do 21 right now. Your graph is f of x equals e to the x squared, and do all the parts. And I'm going to move on and do problem 24. F of x equals 3x e to the x. So the parts that I need to do for 24 are part A, find the domain. And for every e function that we're going to do, the domain is going to be negative to positive infinity. There's going to be no algebra to find the domain. There isn't any feature that would cause the domain to be restricted for any of our e problems. For part B, we're going to find the x-intercepts, or intercept if there's only one of them. And we find the x-intercept by just taking the right-hand side of the function and we set it equal to 0. The function in problem 24 is 3x e to the x. When I take that and set it equal to 0, it's factored. So I'll split each of the factors up and separately set each one of those equal to 0. For the 3x equal to 0, I divide both sides by 3 and get x equal to 0. So that's going to be an x-intercept. The x coordinate is 0, and always when I find an intercept, the opposite letter is 0. So this is an x-intercept. The opposite letter for x for points is y. The y has to be 0. So there's an x-intercept at 0, 0. And for this e to the x equal to 0, there's no solution. So that won't give me a critical number, or an x-intercept, should I say. It wouldn't give me a critical number either, but I'm finding intercepts here. For 24C, I'm finding the y-intercept. And to find the y-intercept, I plug 0 in for all the x's. So I'm going to go f of 0 equals 3 times 0 times e to the 0. I can do that in my head and see that at 0, but if you can't, you would just get to the main screen on your calculator and do 3 parentheses 0 second and ln to get an e with an exponent, and there's my 3 times 0 e to the 0, and that should give me 0. That's the y-coordinate of the y-intercept. The algebra for an intercept gives me the letter that the coordinate of the letter. In this case, I'm finding the y-intercept. That gives me the y-coordinate, and always the opposite letter, its value is going to be 0. So for the y-intercept, the x is going to be 0. For 24D, the asymptotes we're skipping. For all the e functions, we're going to be skipping the asymptote part of it. So I should probably throw this X-intercept and Y-intercept on a graph, because eventually I need to graph. And the graphing is the part K, so I'll call this 24K. I don't know if I labeled the K on the last one. And again, E graphs are usually top-heavy, so I make the positive part of the y-axis more pronounced than the negative part of the y-axis. This point is super easy to plot. It's the point 0, 0. That's both the x and the y-intercept. All right, so now the first derivative calculus part. So for 24e, I need to find out where the graph is increasing. For 24f, I need to find out where the graph is decreasing. In 24g, I need to find any relative maximums and relative minimums. I don't know ahead of time what I have here. So the original function is f of x equals 3x e to the x. I need to find its first derivative. Because there's multiplication, I'm going to use the product rule to find that derivative. So those are the factors that I'm worried about when I'm pulling out my product rule. So for f prime of x, I need each piece's derivative times the other unchanged. So I'm going to take the derivative of 3x times e to the x unchanged plus the derivative of e to the x times the 3x unchanged. The derivative of 3x, because it's a first power term, its derivative is just its coefficient. The coefficient is 3. So the first piece is going to be 3e to the x. For the second piece, the derivative of e to the x is just the e to the x function times the derivative of its exponent. Its exponent is really 1x. It's a first power term. The derivative of any first power term is its coefficient. So the derivative of the exponent 1x is just 1. So that's the derivative of e to the x is just 1 e to the x. And I'm going to bring down this unchanged piece, the 3x. Now I'm going to pull out my common factor. There's a 3 as a common factor and an e to the x as a common factor. So I'm going to write f prime of x equals 3 e to the x times, bring this parentheses down. To the left of the parentheses, I pulled out the factor entirely, so I'll leave a 1 behind. After the plus sign, I have a 1 and an x left over, but I factored out the e to the x and the 3. And 1 times x, I'm just going to write as x. So now this is factored. I'll find the critical numbers by setting this equal to 0. So I'm going to go 3 e to the x times 1 plus x equal to 0. That will cause me to go 3 equal to 0, e to the x equal to 0, and 1 plus x equal to 0. For the 3 equal to 0, it doesn't have an x. It doesn't give a critical number or a solution. E to any power can't equal to 0. That won't give a critical number or a solution. And for this one, I'd minus 1 from both sides and get a critical number of x equal to negative 1. I don't know if I can do the number line stuff on this sheet, but I'm going to try to jam it in here. So for the to finish up this, now that I have my critical number, I'll create a number line that has negative and positive infinity on the edges and my only critical number of negative 1 between the infinities. And now I'm going to create an interval from negative infinity to negative 1, negative 1 to infinity. I need test numbers. In the first interval, all the values here are negative. I need to pick a negative number that's in that interval. I'm going to pick negative 2. In the second interval, it goes from a negative 1 to a positive infinity. 0's in that interval. I'll pick 0. And I'm going to find the sign of f prime of negative 2 and the sign of f prime of 0. If it's negative, it's decreasing. If it's positive, it's increasing. I'm going to enter this function, 3x e to the x, in my y1. I'm going to zoom standard, even though that might not be the best window. And I'm going to use the dy dx to get those values. So now I'm entering y equals, clear out the function that's in there, then 3x second ln e to the x. Zoom standard should be adequate. That's probably not the best window for this graph, but it's good enough for this part. So now second calc dy dx plug in -2 for the x, and I get -0.4. -0.4, it's negative, so the graph is decreasing in that interval, and I'll put a decreasing arrow over my number line. And then for 0, second calc dy dx, type in 0, and I get +3 point something. It's positive, so the graph is increasing in that region, and I'll put a little increasing arrow. Okay, so I can answer a lot of 24 E, F, and G. I can see that it's decreasing in the interval from -infinity to -1. It's increasing in the interval from -1 to infinity. And immediately when I look at my arrows, I can see there's a minimum point, and its x value is -1, and there's no maximum point. So for the relative maximum, I'm going to write none. For the minimum, I can say there's a relative minimum of y equal to something, which occurs when x equal to -1. To get the y value on my calculator probably isn't going to be suitable, but if I want to get a y value of a point using my graphing screen, I go second, calc, hit enter on value, type the x value of -1 that I want to get the y value for, and my calculator gives me -1.103638. I don't want decimal y values. This means I probably going to have to do this by hand. To get the y value by hand, I'm going to use the original function and find out what its y value is. So I'm going to find f of -1 using the original function, which is going to be 3 times -1 times e to the -1. 3 times -1 is -3, and I'm going to get the e to the -1 to have a positive exponent by creating a fraction and moving it down to the denominator of the fraction. The y-coordinate is going to be -3 over e to the first, which I'm just going to write as -3 over e. So let me check to make sure my y-coordinate matches up with the y-coordinate of the minimum, the decimal version, by going to the main screen and doing -3 divided by e. It better equal that number. So -3 divided by, if you just want an e without an exponent, you just hit the second and the divide key. And I get exactly the same value. So this is a proper way to answer the relative minimum. When I go to graph it, I have to kind of think of a point. Let me transfer the information that I just figured out here onto this sheet, so when I graph it, I know what to do. So this is going to be increasing from -1 to infinity. It's decreasing from -infinity to -1. And when I go to graph the minimum, I probably think of it as a point. And as a point, its x value is -1, its y value is -3 over e. So the x value is -1, the y value is -3 over e. And -3 over e isn't something I can plot so well. When I go to plot it, I think of the decimal version, I'll just say -1.1. And so on my graph now, I can do a little bit of work here. I can graph the minimum point, but I'm not going to graph the increasing and decreasing before I know the concavity. So I'm going to mark -1 on the x-axis, and then -1 and -2 on the y-axis. And I'm going to plot the point -1, -1.1, and I'm going to call that the point -1, -3 over e. When I look at the graph on my calculator, somewhere over there is that minimum point that I need to know. Okay, so that's all the increasing and decreasing stuff that I can do before I jump into the concavity stuff. So the next few things that I need to do problem 24H, any intervals where the graph is concave up. 24I, any intervals where the graph is concave down. And 24J, any inflection points. And to do concavity, I need the second derivative. Second derivative is not going to be so nice to do. The original function is f of x equals 3x e to the x. The first derivative, I need some form of the first derivative. I think the factored form is going to be the nicest. I'm going to write 3 e to the x times 1 plus x as the first derivative. I'm going to write 3 e to the x times 1 plus x as the first derivative, because that's what the factored form of the first derivative. To find the second derivative is a little bit of work. Because the first derivative has multiplication, I'm going to use the product rule. And I don't need to separate the 3 from the e to the x because it doesn't have an x. So I'm going to use the product rule, and those are the two factors I'm going to use in the product rule. So now I'm going to write f double prime of x, and the product rule, I'm going to take the derivative of 3 e to the x times the 1 plus x unchanged, plus the derivative of 1 plus x times the 3 e to the x unchanged. To do the derivative of 3 e to the x, because the 3 doesn't have an x, I'm just going to leave the 3 out in front of the derivative of e to the x. And the derivative of e to the x, you write the e to the x function down, and to the left of it, you write the derivative of its exponent. Its exponent is a first power term, so the derivative is its coefficient, and its coefficient is 1. So the derivative of 3 e to the x, I could have used the product rule, but because the 3 didn't have an x, I could just tag the 3 onto and multiply it by the derivative of e to the x. So the derivative of 3 e to the x is just 3 e to the x. And I'm going to bring down the 1 plus x. That doesn't change on that part. Bring down my plus sign. The derivative of that parentheses 1 plus x, the 1 is a constant, its derivative is 0. The x is a first power term, its derivative is its coefficient, and its coefficient is 1. Bring down the 3e to the x, and that's going to be the derivative of the second derivative unmultiplied out. Let me multiply this 3 and 1, and you get a 3e to the x times 1 plus x plus 1 times 3e to the x. I don't know why I switched the parentheses to the e to the x rather than the 1 there, but I did. It's not wrong. So my common factor is a 3e to the x. I'm going to pull out that common factor. I get f double prime of x equals 3e to the x. I'm going to write a parentheses, bring this plus sign down. To the left of the parentheses, I have a 1 plus x. It's in a parentheses. I'll drop the parentheses in a second. To the right of the plus sign, I have a 1. So this is going to give me f double prime of x equals 3e to the x times 1 plus x plus 1. The parentheses 1 plus x I can drop without doing any changing. And this gives me f double prime of x equals 3e to the x times x plus 2. That's my second derivative. To get critical numbers, I take the second derivative and set it equal to 0. So I'm going to take that second derivative and set it equal to 0. I'm going to go 3e to the x times x plus 2 equal to 0. The 3, because it doesn't have an x, you can leave it with the e to the x, or you could separate it from the e to the x. It's not going to impact the critical numbers that we're getting. When I do 3 equal to 0, it doesn't have an x, it doesn't give a solution, nor does it give a critical number. When I set e to the x equal to 0, it doesn't give a solution, it doesn't give a critical number. And when you set x plus 2 equal to 0, you get x equal to negative 2. So the only critical number is negative 2. I'm going to create a number line and put negative infinity and positive infinity on the edges, negative 2 between, and create my intervals, negative infinity to negative 2, negative 2 to infinity. In each interval, I need to pick a critical number. In the first interval, I'm going to pick x equal to negative 3. In the second interval, because it goes from negative to positive, I'm going to pick 0. I'm going to find f double prime of negative 3, and I'm going to find f double prime of 0. I need to know what f double prime is, and this is the best version of f double prime. So to do f double prime of negative 3, I'm going to take all those x's in there and change them to negative 3. So I'll go 3e to the negative 3 times negative 3 plus 2. In a second, I'll do that on my calculator. For 0, I'm going to go 3e to the 0 times 0 plus 2. Both of those I can't do from the dy dx screen or the graph screen because it doesn't do second derivatives, it does first derivatives. Let me just do these real quickly on my calculator. So first computation, get to the main screen, 3 second ln negative 3, and then times parentheses negative 3 plus 2 plus 2. I'm only worried about the sign of this, and that's negative 0.15. It's negative, so the graph is concave down in that interval. For the other computation, 3 second ln e to the 0 times parentheses 0 plus 2, I get 6. Wow, that was surprising. It's positive, so the graph is concave up in that interval. So the graph is concave down in the interval from negative infinity to negative 2. It's concave up in the interval from negative 2 to infinity. And anytime a graph changes concavity, if the function is defined at that value of x, you get an inflection point there. The x coordinate of my inflection point is going to be negative 2. Let me transfer this to my answers. So the graph is concave up in the interval from negative 2 to positive infinity. It's concave down in the interval from negative infinity to negative 2. And I get an inflection point, and the x coordinate of the inflection point is negative 2. If I want to find the y coordinate of the inflection point, I could attempt to use the value screen on my calculator. So if I did if I just graph the function and do second calc value and type in negative 2, if that gives me something that's not a decimal, then I'll throw that in and call that the y coordinate of the point that I need. Since it is a decimal, it's not adequate, and I think I have to do this by hand. So to get the y coordinate of the inflection point by hand, I'm going to find f of negative 2, which involves plugging negative 2 into the original function for x. That's going to be 3 times negative 2 times e to the negative 2 power. 3 times negative 2 is negative 6. E to the negative 2 power can be made e to the positive 2 power if you put it in the denominator of a fraction. The y coordinate of my inflection point is negative 6 over e squared. And if I want to make sure I'm right, I'm going to type negative 6 over e squared on the main screen and make sure it equals that value. So second quit, negative 6 divided by second ln e squared. If it equals negative 0.812, then I did fine, and that's inflection point is correct. All right, so I'm ready to finish the problem up with my graphing, and the information that I need to make sure the graph shows is the graph is concave up from negative 2 to infinity. It's concave down from negative infinity to negative 2, and it has an inflection point at the point negative 2, negative 6 over e squared. And again, that negative 6 over e squared, when I go to graph it, I'm going to graph like negative 0.812. So right now, I'm going to plot the inflection point, which is x equal to negative 2, y equal to negative 0.812. And negative 0.812 is just above negative 1. So that point right there is the inflection point of negative 2, negative 6 over e squared. That's the inflection point. This point's the relative min. Look at my inflection point and my relative min. Just had a glitch. When I look at my inflection point and my relative min, their y's are very small. I can probably get a better graph if I change my y's to a smaller number. So I'm going to change my window, and I'm going to change my y's to 3s. Or I could have changed them to 1s, just because the y coordinates of the inflection point and the relative minimum were decimals. I'll probably get a better graph if I make my y smaller than the 10s. Now I'm going to copy that graph onto my calculator and make sure that it does what it's supposed to do. It kind of looks to me like the x-axis is a horizontal asymptote here. If we did the part with the asymptote, I would have showed you something from Calc 2 to find that horizontal asymptote, but we won't. I'm just going to copy my graph, and it looks like over here that the graph doesn't disappear. It just gets so close to the x-axis you can't see it. So I'm going to graph something in my first interval. It's going to be from negative infinity to this point right there. It's concave down, and it's decreasing all the way from the left edge of the x-axis to the minimum point. So here my graph is decreasing, 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 and concave down. And then it gets to the inflection point. At the inflection point, it starts being concave up, but decreasing still. So right here, I'm going to flip it over. It's changing concavity. So the first half is decreasing and concave down, gets to the inflection point. It stays decreasing and flips to concave up, goes through both the inflection point and the minimum point. For the rest of the graph, once it gets to the minimum point, it's going to start increasing, and it's going to continue to be concave up, and it has to go through the point 0, 0, which is both the x and the y-intercept. And that's more or less what my graph looks like on my calculator. I'll put little arrows to signify the graph keeps going. So that copying I just did, I didn't do any real creativity here, other than I made sure my graph was concave down and decreasing till it got to the inflection point. At the inflection point, it didn't change to increasing. It stayed decreasing, but it flipped to concave up. Once it gets to the inflection point, it's going to turn around and start increasing. It's going to stay concave up and going to go through the intercept. And that's a perfect graph for 24. So you should take a minute to try to do problem 23. I guess it's more like 20 minutes to do problem 23. And I'm going to do one more E problem, and then we'll call that the end of this video. And as I look at the E problems, let's make a vote to skip 27 and 28. And just because they're a little bit different, and I don't want to get too different with my problems, and I'm going to make a stab at doing 26, and you'll do 25. So you're going to skip 27 and 28 when you do the homework here. If you want to give them a try, you can. I've got solutions written up, and you can certainly give it a try if you feel ambitious. So let's go in for 25 and 26. I'll do 26. You should do 25. So for 26, the first thing I need for 26a is the domain. And for all our E functions, there isn't anything given in the function that will cause the domain to be anything other than negative to positive infinity. Specifically, there aren't any fractions with x's in the denominator. There aren't any square roots. There isn't anything that would cause a domain to be restricted. And that will be the case if I give you an E problem on the test, that its domain will also have no algebra to find. Part B, I need to find the x-intercept. You find the x-intercept by taking the function and setting it equal to 0. So this is factored. If I want to, I could separate the 2 from the x squared, or I could leave the 2 with the x squared when I go to find my x-intercept. Setting the factor of 2 equal to 0, because it doesn't have an x, doesn't give a solution. And any factor with an exponent, if it's set equal to 0, you can just drop the exponent and set that factor itself equal to 0. And x squared equal to 0 will give me x equal to 0, because the only number squared that's 0 is 0. That's an x coordinate of an x-intercept. And always the letter that's unnamed, y is unnamed, its coordinate has to be 0. The opposite letter always has a 0 for its coordinate. And for the e to the x equal to 0, we know that gives no solution. So the only x-intercept is going to be the origin point 0, 0. I'll plot that in a second, but let me do the y-intercept before I actually start my graph. For the y-intercept, I'm going to plug 0 in for the x's into this function. So I'm going to go f of 0 equals 2 times 0 squared times e to the 0. I know that 0, I can do it in my head. If you're not comfortable doing that in your head, you can go to the main screen of your calculator, go 2 parentheses, 0 squared, and then second ln e to the 0. And it's going to give you 0 for the y part of the y-intercept. Always the algebra gives you the letter, the coordinate of the letter that we're looking for. I'm looking for the y-intercept. The algebra gave me y equal to 0. And always the letter that has the opposite name gets 0. So the x part of the y-intercept is 0. So the only point that I have to graph on problem 26 is the origin 0, 0. And my guess is most of these E functions, their graphs are more top-heavy than anything. They usually don't dip too far below the x-axis. So I'm going to plot the point 0, 0 as my x-intercept. Now I'm going to move on and do the increasing, decreasing, maximum, and minimum part. And I really need a whole sheet of paper for that. So for 26E, where the graph is increasing, for 26F, where the graph is decreasing, and 26G, any relative maximums and relative minimums, I'll do those on a separate sheet of paper. I need to take the original function and find its first derivative. Because there's multiplication, when I go to do the first derivative, I need to use the product rule. There's multiplication and both terms have an x. That makes me destined to use the product rule. So for my derivative, f prime of x, I'm going to get the derivative of 2x squared first. Oh, the derivative of 2x squared times the e to the x function plus the derivative of the e to the x function times the 2x squared function unchanged. The derivative of that 2x squared, you just multiply the 2 by 2 and get 4, lower the exponent by 1. The derivative of 2x squared is 4x. I'm going to multiply that by the e to the x function. And then plus the derivative of any e function is just that e function times the derivative of its exponent. The exponent is 1x. Its derivative is just 1. And I'm not even going to write that 1, but I could write a 1 preceding that e function. And then I'll bring down the 2x squared. That doesn't change. Common factor has a 2 between that 4 and that 2. It has an x to the first power between that x and that x squared, and it has an e to the x between the e to the x's. So I'm going to go f prime of x equals 4x e to the x, oh my gosh, times, and then here I took the factor out completely. I'll leave a 1 behind. I'll bring this plus sign down. Took out that e to the 2x squared. Oh, I made a mistake here. Let me fix it before it's too late. My common factor I said was a 2 from that 4 and that 2. I can't pull a 4 out. An x between that x and that x squared, and e to the x between the two e to the x's. Now, from the first term, I factored out a 2. There was a 4 there. I'll divide that 4 by 2 and get a 2. The x I factored out, the e to the x I factored out. I'm going to bring my plus sign down. And to the right of the plus sign, I factored out the e to the x. I factored out the 2. I factored out 1x from the x squared. And I'm just going to be left with a single x. That's factored. And when I look at this, it's fine in terms of doing the work that I need to do with the first derivative. If I want to find the second derivative, it's going to be a disaster. So in this problem 26, I'm going to skip the concavity stuff, and you can skip on problem 25 the concavity stuff. So I'm going to skip 26H through J. This is the concavity stuff. It's doable, but it's probably would take me a good 20 minutes to do it, maybe 25 minutes to do it, and I don't think that's very productive use of our time. So similarly, when you do 25, you're going to skip the concavity. Just like I did on some of the graphs, when the second derivative gets a bit ridiculous to compute, it's just not probably a good use of our time. Our algebra skills don't need to be that refined. In a Math 220 calculus, you need probably a little bit higher level calculus skills because you have to take Calc 2 and Calc 3, and your algebra skills maybe need to be at a slightly more elevated level, but this would be ridiculous. It wouldn't be productive for us. It's just going to be more confusing than helpful. So getting back to my maximum and minimums, increasing and decreasing, this first derivative is factored. I'm going to set it equal to 0, and I'm just going to set the 3 factors equal to 0 just to save myself a line of writing, because when you set the whole thing equal to 0, you split the factors up and set them equal to 0. For the 2x factor, when I set it equal to 0, I'll divide both sides by 2. That's going to give me a solution of x equal to 0. For the e to the x equal to 0, you don't get a solution for that. And for the 2 plus x equal to 0, you'll minus 2 from both sides and get x equal to negative 2. So I've got two numbers along with the infinities to throw on a number line. So this would be a pretty complex graph. So when I go to do my work here, I'm going to put a negative infinity and positive infinity on the edges of my number line, and a negative 2 and 0, the critical numbers between those. I always get one more interval than critical numbers, so I'm going to get 3 intervals because I had 2 critical numbers. My intervals are going to be negative infinity to negative 2, negative 2 to 0, and 0 to infinity. And each interval I need to pick a number and plug it into the first derivative, and I'll use my dy dx feature on my calculator. And in order to use the dy dx feature on my calculator, I have to have the original function entered in my y1. My original function is 2x squared e to the x. So on y equals clear 2x squared second ln e to the x. I'm going to zoom standard. Probably is not the best window, but it's going to be adequate to answer what we need for this. Yeah, I'm probably going to crunch my y's again. The y coordinates are probably going to be really small again. Had I left that last window at the 3's, it might even look better. Let me just show you. If I made the y min negative 3 and the y max positive 3, the graph that I get is probably better than if I didn't. So let me find these values now. So I'm going to do f prime of negative 3 by going second calc dy dx. I type the number negative 3, and instead of writing the number, I'm just going to write positive and increasing. I don't really need to write the number down. I've been writing it down all along, but it's really kind of a waste because I just need to know the sign. Middle interval, second calc dy dx, type in negative 1, and I get negative point something. And again, I don't really care so much that it's negative 0.7357. The fact that it's negative tells me the graph is decreasing in that interval. And in the last interval, second calc dy dx, type in 1, and I get 16. I get a positive number. I don't know, just instinctively wanted to write that number down. But it doesn't, when you go to the test, if you just wrote positive and negative and didn't write the number down, that would be completely adequate. So, write my little arrows. It's increasing, decreasing, increasing. I'll transfer those to my answers, and I can see I have a maximum point and its x-coordinate is negative 2. I have a minimum point and its x-coordinate is 0. So when I go to do my answers for this problem, I'm going to say it's increasing from negative infinity to negative 2, and then union 0 to infinity. It's decreasing from negative 2 to 0. And then I have a relative maximum of y equal to some number which occurs when x equal to negative 2, and I have a relative minimum of y equal to some number which occurs when x equal to 0. My calculator will give me decimal equivalents, which are going to be helpful for graphing. So let me find the y coordinate when x is negative 2 and when x is 0 by going second calc value, typing negative 2. The y coordinate when x is negative 2 is 1.08. And so I'm just going to write right above this answer 1.08 because I'm going to need it when I graph. And for the relative min, do second calc value x equal to 0. And that gives me y equal to 0. That computation is good enough. I don't need to do anything extra for it. So my relative minimum is going to be at the 0.00. For the relative maximum, the original function is f of x equals 2x squared e to the x. I need to plug negative 2 in for x and do f of negative 2 equals 2 times negative 2 squared times e to the negative 2. That's going to be 2 times 4 e to the negative 2. 2 times 4 is 8. And to make the e to the negative 2 have a positive exponent, I'll create a fraction and throw it in the denominator. That 8 over e squared goes in my answer for the relative maximum. So there's a relative maximum of 8 over e squared, which occurs when x equal to negative 2. I should make sure 8 over e squared equals 1.08 by going to my main screen and doing 8 divided by second ln e squared. And it better be that 1.08, which it is. So I have all this information for the increasing and decreasing the maximums and minimums. I'm skipping the concavity because it's a bit ridiculous. I'm going to transfer this information over. I'm going to transfer that it's increasing from negative infinity to negative 2 and 0 to infinity. It's decreasing from negative 2 to 0. I have a relative maximum, and I'm going to write it as a point. It's easier when I graph to think of a point. It's going to be the point negative 2, 8 over e squared, max, negative 2, comma 8 over e squared. And that 8 over e squared is 1.08. And I have a relative minimum, which is going to be at the point 0, 0. So I'm going to plot the maximum and the minimum point, and then I'm going to borrow the graph from my calculator with that refined window. So I need to plot this point, which is negative 2, 1.08. And so negative 2, 1.08 is just about there. I'm going to call that the point negative 2, 8 over e squared. I needed to plot the point 0, 0. It's already plotted. Now all I'm going to do is borrow from my calculator the graph and make sure it does what it needs to do, meaning it increases where it needs to increase, decreases where it needs to decrease. So I already have the function in there, I believe, 2x squared e to the x. I had the window on the 10s on the x's, 3s on the y's. I got this for a graph. Looks like there's a horizontal asymptote again at the x-axis. I didn't do any asymptote work because that involves calculus that we don't teach in this class. And I didn't do concavity, but it looks to me like the graph was concave up for a bit, and somewheres between the start of the graph and the maximum, it switches concavity. I don't know what that point is. There is an inflection point there where it goes from concave up to concave down, but I can't. The algebra, the calculus would have been too much. So it increases. It probably uses the x-axis as an asymptote, gets to the maximum point, and it turns over and starts decreasing between the maximum point and the minimum point. As I look at my graph, it looks like it goes from concave down to concave up. Looks like there's another inflection point that we don't have to find. Once it gets to the minimum point, it shoots up and increases forever. That looks like a reasonable graph because it's increasing from negative infinity to negative 2. At x equal to negative 2, it turns around, starts decreasing to x equal to 0, then it increases. It goes through the maximum point, it goes through the minimum point, which is also the x and the y-intercept. I threw some concavity in there and made little points where the graph changes concavity, but I have no idea what the coordinates of those points are. So that should be all we have to do for e functions. We just have ln functions left to deal with, which will be in a part 4 for our video. So go ahead and give 25 a go, and I'll stop the video now and sit and watch it, and hopefully it's okay.